In the quantum world, the idea that particles behave as both waves and discrete units reshapes everything we thought we knew about reality. When scientists first explored atomic and subatomic behavior, they expected particles to act like tiny solid objects, little dots that move through space in predictable paths. But as experiments grew more precise, a strange pattern emerged. Electrons, photons, and other fundamental entities refused to fit into this simple category. Instead, they displayed a dual nature, sometimes behaving like particles localized, countable, and measurable, and at other times spreading out like waves, filling regions of space with possibilities rather than fixed positions. This wave-like behavior becomes visible in experiments such as the double-slit experiment, where single particles sent one at a time create interference patterns usually produced by waves. It is as if each particle travels through multiple paths simultaneously, exploring all available possibilities before settling into a final state when measured. Yet the same particle can also collide, strike, or be counted in detectors in a way that proves it exists as a discrete packet of energy. This duality is not a contradiction, but a deeper message from nature. The quantum world does not follow the simple categories of either or. It holds both descriptions at once, revealing that particles are not objects in the classical sense, but expressions of underlying wave functions that encode probabilities and potential. In this mysterious behavior, we find a bridge between the intangible and the concrete. The wave aspect represents potential, a map of everything a particle could be or where it could appear. The particle aspect represents the realized outcome, the moment when one possibility becomes actual. This duality does more than define the quantum world. It challenges us to rethink the nature of existence itself, showing that reality is not fixed but shaped by deeper, invisible patterns that govern every level of the universe. In the quantum world, the act of observing is not a passive experience, but an active event that influences what can be known and what becomes real. This idea emerges from countless experiments where particles, when left undisturbed, exist in a state of possibilities, spread out like waves across multiple paths and outcomes. But the moment a measurement is made, these possibilities collapse into a single, definite result. It is not that the observer's mind changes reality. It is the physical interaction involved in measurement that forces the system to choose one path out of many. Observation in quantum mechanics is simply another name for interaction, an exchange of energy or information that leaves a trace and demands a clear outcome. This effect can be seen in the famous double-slit experiment, where particles create interference patterns when not observed, acting like waves that explore all available routes. But when detectors are placed to observe which slit each particle passes through, the interference pattern disappears, and the particles behave as if they have taken only one path. The measurement changes the behavior, not because of any magical influence, but because the measuring device becomes part of the system, altering the delicate quantum state. The act of observing breaks the fragile superposition of possibilities and forces the particle to behave in a definite way. This principle reveals something profound about nature. Properties do not exist as fixed facts waiting to be uncovered. They emerge through interactions. Position, momentum, and even the path a particle takes are not predetermined but shaped by the conditions under which they are measured. This challenges our classical intuition, where observing something simply reveals what was already there. In the quantum world, observation is a creative act, shaping the very outcome it seeks to understand. It reminds us that the universe at its smallest scales is not a collection of independent objects, but a dynamic interplay where the observer and the observed are deeply intertwined. Entanglement reveals one of the most astonishing truths about the quantum world. Particles can become so deeply connected that they behave as a single system, even when separated by vast distances. When two particles interact in a certain way, their properties become linked, forming a shared state. After this connection is formed, whatever happens to one instantly affects the other, not through signals or physical contact, but because they are no longer truly separate in the way classical physics imagines. They exist as parts of one unified quantum state, and measuring one particle immediately defines the condition of its partner. This phenomenon has been demonstrated in countless experiments. When scientists measure the spin or polarization of one entangled particle, they find that the second particle's corresponding property becomes determined at the same moment, even if they are far apart. It is not that information travels between them faster than light. Rather, both were never independent to begin with. They share a single identity that stretches across space, and the measurement simply reveals the structure of that shared identity. Entanglement challenges our understanding of separation, signaling, and locality. In the everyday world, distance creates independence. Objects separated in space behave independently. But entanglement shows that quantum systems can remain connected beyond space, as if distance loses meaning at the deepest level of reality. This connection hints at a universe far more unified than our senses suggest, a universe where relationships, not individual parts, form the foundation of nature. It suggests that wholeness is not just a philosophical idea, but an unavoidable feature of the quantum fabric that shapes all physical existence. Quantum mechanics reveals that the smallest parts of the universe cannot be understood in isolation. They only make sense as elements of a larger whole. When scientists examine individual particles, they often find that these particles display behaviors that seem incomplete or contradictory when viewed alone. But when the same particles are studied within the context of the systems they belong to, their behavior becomes clearer. A particle's properties, its energy, momentum, spin, or even its position, do not exist as fixed, independent characteristics. They arise only when the particle interacts with its surroundings, making the system itself the true source of meaning. This understanding shifts our focus from isolated objects to interconnected processes. In classical physics, the world is explained by breaking systems down into their smallest parts and studying each piece separately. But in the quantum world, this approach fails because the parts are inseparable from the whole. A quantum system behaves as a unified entity, where the state of each component depends on the state of every other component. Changing one part influences the entire structure, even across distance, revealing that quantum systems resist fragmentation. The whole defines the parts, not the other way around. This perspective transforms our understanding of reality. Instead of thinking of the universe as a collection of tiny, independent particles, the quantum view presents it as a web of relationships where meaning emerges from interaction. Objects become less like standalone entities and more like nodes in a vast network of connections. This wholeness is not an abstract idea, but a measurable truth, shaping how quantum systems evolve, respond, and exist at the most fundamental level. Quantum mechanics teaches us that interaction sits at the very heart of physical reality. Nothing in the quantum world possesses a complete, measurable property on its own. A particle does not carry a fixed position, a definite momentum, or a predetermined spin as an independent badge of identity. Instead, These characteristics arise only in the moment of interaction, when the particle meets another particle, a field, a detector, or any external influence capable of exchanging energy or information. This idea transforms our understanding of nature at its deepest level. Instead of imagining the universe as a collection of tiny, self-contained objects moving through empty space, quantum theory shows us a world woven from encounters and exchanges, where outcomes are shaped by the relationships between things rather than the isolated things themselves. When we look closely at a quantum system before any interaction occurs, we find not certainty but possibility. A particle can exist in a superposition, occupying many potential states at once. It may be found in several places simultaneously, holding multiple energies or even multiple spins. These are not hidden facts waiting to be uncovered. They are genuine states of potential, describing what the system could be rather than what it is. But the moment the particle interacts with something, a measuring device, a photon, a neighboring particle, this cloud of possibilities condenses into a single measurable outcome. Impossible to that world is SI-MPLE, for OUTOME does not reflect a pre-existing value but a value created through the interaction itself. Interaction does not merely reveal reality, it shapes it. This principle became clear through decades of experiments, where the behavior of particles depended entirely on the situations in which they were measured. In the double-slit experiment, for instance, electrons act like waves when no measurement is made to determine which path they take. They spread out, explore multiple routes, and create interference patterns that reveal their wave, like potential. Yet, once detectors are placed to measure which slit each electron passes through, this delicate wave pattern collapses, and the electrons behave like localized particles. The very act of interacting with the detectors forces the system to abandon its multiple possibilities and choose a single trajectory. This behavior is not a flaw in our instruments, but a fundamental aspect of quantum nature. Measurement is an interaction, and interaction alters the system. In more complex systems, such as those involving entanglement, the role of interaction becomes even more profound. Two particles that once interacted can remain connected long after they separate. Their properties remain correlated, as if they are pieces of a single entity stretching across space. This lasting connection is not a passive memory, but an active feature of the system. It shows that interaction leaves an imprint, weaving particles into shared states that defy classical separation. The wholeness created by interaction cannot be undone simply by distance. The relationship becomes part of the identity of the particles themselves, shaping their behavior in all future measurements. In quantum field theory, which extends quantum mechanics into a more complete framework, the importance of interaction becomes even clearer. Particles are no longer seen as isolated points, but as excitations of underlying fields that fill all of space. What we call a particle is simply a ripple or vibration in these fields, and these ripples interact through the exchange of other excitations. Forces are interactions. Motion is interaction. Even the existence of a particle in one location versus another depends on interactions with the fields and vacuum energies around it. Reality becomes a continuous dance of fluctuations and exchanges, where every measurable property is born from the way one excitation influences another. This deeper view of interaction also explains why quantum systems are extremely sensitive to their environment. Any interaction, no matter how small, can disturb the delicate balance of superpositions and entanglements. A tiny exchange of energy or a minute scattering of a photon can be enough to collapse superposition or destroy entanglement. This sensitivity is not weakness, but a defining trait of the quantum world. It reveals that quantum states are relational. They do not exist independently, but depend on the conditions that surround them. A quantum system isolated perfectly from its environment would behave very differently from one constantly interacting with air molecules, light, or thermal radiation. But perfect isolation is almost impossible to achieve, which is why quantum behavior is rarely visible in the everyday macroscopic world. Interaction with the environment forces quantum systems to behave classically, losing their delicate probabilistic nature and adopting definite, predictable outcomes. This process, known as decoherence, is another demonstration of how interaction defines quantum properties. Decoherence occurs when a quantum system interacts with countless particles in its surroundings, causing its superpositions to spread out and become entangled with the environment. As these interactions multiply, the system loses the ability to maintain coherent multiple possibilities. Instead, it settles into classical outcomes because the environment has effectively measured it. Once again, interaction determines the behavior, showing that the classical world we experience is not separate from quantum laws, but emerges from them through constant interaction. At the foundation of quantum measurement lies a principle that has puzzled physicists for generations. A property such as position or momentum cannot be assigned a definite value until an interaction occurs. Before that moment, the particle does not hide the value. It simply does not possess it. Quantum mechanics teaches that properties are not intrinsic features, but contextual results. A position is defined only relative to something else, a detector, a coordinate system, or a physical boundary. A momentum is defined only when there is a way to measure the change produced by interaction. Quantum properties are therefore not absolute but relational. They belong not to the particle alone, but to the interaction between the particle and the world around it. This relational nature has philosophical implications that stretch far beyond physics. It challenges the idea that the universe can be fully understood by dividing it into isolated parts. Instead, it suggests that meaning arises through connection. A particle becomes real, in a specific way only when it interacts. Until that moment, it carries multiple potentials. The universe is not built from predefined objects, but from interactions that create structure, behavior, and outcome. Reality becomes less like a collection of bricks and more like a web of encounters, where each point of connection adds to the unfolding pattern. In this perspective, even the concept of identity begins to shift. A quantum particle cannot be described fully as a thing with fixed properties. It is better understood as an event, a momentary expression of a field, shaped entirely by how it interacts with other fields and systems. The properties we assign, position, spin, charge, are descriptions of how the particle participates in the world, not descriptions of what it is in isolation. Yet this is not limited to particles. It reflects a universal principle. Stars, galaxies, atoms, and human bodies are arrangements that gain their structure through constant interaction. Gravity binds celestial bodies. Electromagnetic forces bind atoms. Biological systems survive through chemical interactions. The principle that interaction defines properties extends from the tiniest quantum scale to the largest cosmic systems. On a practical level, quantum interaction is the foundation of modern technology. Every laser, every transistor, every MRI machine relies on the principles that quantum states change through interaction. Quantum computing takes this further, using superposition and entanglement to create machines that process information through controlled quantum interactions. The act of manipulating qubits quantum bit relies entirely on precise interaction with fields, particles, and electromagnetic pulses. If interaction did not define quantum states, none of these technologies would be possible. The stability, reliability, and behavior of qubits depend on controlling how they interact, both with each other and with the surrounding environment. Too much interaction destroys the quantum state. Too little prevents computation. Balancing these interactions is the essence of quantum engineering. Furthermore, the study of interaction reveals why some particles exist at all. In quantum field theory, particles appear and vanish in the vacuum due to fluctuations. These temporary particles interact with real particles, altering their mass, charge, and behavior. Even something as fundamental as the mass of the electron is not an isolated property. It is shaped by interactions with other fields, including the Higgs field. Without interaction, mass would not exist in its recognizable form. This insight bridges quantum mechanics with particle physics, showing that interaction defines both the properties of particles and the forces governing them. The idea that interaction shapes reality does not diminish the role of objects, it enriches it. It tells us that things are not static but dynamic, constantly influenced by their surroundings. The universe is not a set of still images but a moving, evolving tapestry of relationships. Every atom, every photon, every fluctuation contributes to the unfolding pattern through its interactions. Nothing exists alone. Every property, every event, every measurement is the result of connections that stretch across space and time. As we explore deeper, we find that interaction is not just a feature of the quantum world. It is the organizing principle of existence. The classical world arises from quantum interactions multiplied across countless scales. The stability of matter, the flow of energy, the formation of stars, and even the emergence of life all depend on networks of interaction shaping outcomes at every moment. In this understanding, the universe begins to resemble a living process rather than a static structure. It is self-updating, self-defining, and continuously shaped by the interactions that take place within it. What appears stable is simply the result of interactions that have reached equilibrium. What appears chaotic is the result of interactions that are still unfolding. Reality becomes an ongoing dialogue between systems, where each interaction adds a new layer to the cosmic story. At the quantum level, the smallest exchange can rewrite the fate of a particle. At the cosmic level, the interaction of galaxies can reshape the structure of the universe. Whether on the scale of electrons or galaxies, interaction defines what is real. It does not merely influence outcomes, it creates them. In this sense, quantum mechanics does not describe a world of objects, but a world of relationships, where each connection writes a new line in the script of existence. This view not only deepens our scientific understanding, but also offers a new way of imagining the universe itself. A universe built from interaction is a universe built from connection. It is a place where no part is truly separate, where the boundaries we perceive are temporary, and where the essence of reality lies in how things relate rather than what they are alone. Through this lens, quantum mechanics becomes more than a technical framework. It becomes a profound reminder that at every level, physical, cosmic, relational, the world is shaped by interaction, and through interaction, it finds its form, its behavior, and its meaning. At the quantum level, classical logic breaks down and reveals its limitations, forcing us to rethink the very structure of reality. Classical physics is built on certainty, where objects have definite positions, definite momenta, and follow predictable paths. It assumes that the world can be understood by dividing it into solid pieces and assigning each piece fixed properties. But the quantum world refuses to fit this rigid structure. Instead of certainty, it presents probabilities. Instead of fixed values, it offers superpositions. Instead of independent objects, it shows systems that remain interconnected even when physically separated. Classical logic expects things to be either one way or another, but quantum mechanics shows that nature often exists in multiple states simultaneously until an interaction forces a single outcome. This breakdown of classical assumptions becomes clear when we examine phenomena like wave, particle duality, superposition, and entanglement. A particle behaving as both a wave and a point, like object vile, its classical categories. A system existing in many states at once violates the classical idea that something must possess one clear identity. Entangled particles defy classical separation by behaving as one unified state regardless of distance. These behaviors make no sense under traditional logic, yet they consistently appear in experiments, proving that quantum reality demands a new way of thinking. Even the idea of causality becomes more nuanced in the quantum world. In classical logic, causes always precede effects in clean, linear sequences. But quantum processes sometimes interact in ways that make the order of events ambiguous, or where outcomes depend on probabilities rather than fixed chains of cause and effect. This does not mean that the universe is chaotic. Rather, it follows a deeper logic that classical reasoning is not equipped to handle. Quantum mechanics teaches us that the universe cannot be fully understood using the rigid frameworks we inherited from everyday experience. It reveals a world where uncertainty, probability, interaction, and connection shape reality far more fundamentally than classical logic ever imagined. Quantum wholeness suggests that the universe is not a collection of isolated objects, but an interconnected fabric where every part is linked to every other in subtle and profound ways. At the quantum scale, this interconnectedness becomes impossible to ignore. Particles that seem separate in space behave as if they are part of a single, unified system. Their properties do not belong solely to them, but are shaped by the context in which they exist. This idea stands in stark contrast to the classical view, where the world is built from independent pieces that can be examined separately without losing meaning. Quantum mechanics reveals that separation is often an illusion created by the limits of our perception. When scientists study quantum systems, they find that the behavior of each component depends on the entire arrangement. Change the conditions of the environment, and the properties of the particle shift. Alter the whole system, and the parts transform. This influence is not merely a surface effect, but a fundamental feature of quantum reality. Even the act of measurement, something as simple as detecting a particle, connects the measuring device, the particle, and the larger environment into a single event. No part can be understood without acknowledging the role of the others. Entanglement offers one of the clearest demonstrations of wholeness. When two particles become entangled, their identities merge into a shared state. They may be separated by kilometers or even light years, yet they behave as one. The measurement of one instantly defines the condition of the other, not because of some hidden communication, but because they were never truly separate systems. Their wholeness exists beyond space, revealing a level of unity that defies classical boundaries. This interconnected nature of reality extends far beyond simple particles. Fields, energies, and forces tie together everything in existence. What appears as empty space is filled with quantum fluctuations connecting distant regions. Systems that seem distinct atoms, molecules, biological structures emerge from layers of interaction and coherence built over time. Quantum wholeness invites us to see the universe not as a scattered set of objects, but as a living, evolving web where every event resonates with countless others. It shows that the fundamental structure of reality is unity, and that the deep fabric of existence is woven from relationships rather than things.